Thank you very much for joining us today. It is my great pleasure to welcome you to the third session of the ACT-SAF series, technical trainings delivered under the ACT-SAF program. My name is Jane Hoopy. I am the director in charge of the ICAO Environment Program, and I'm here with the ICAO officers working on ACT-SAF from headquarters and the regional offices of ICAO. This series has been developed following ICAO's engagements with many states participating in the ACT-SAF program, which highlighted the need to level up the understanding of SAF. I'm pleased to see you again participating in high numbers, which is a testimony of the sector's interest in SAF and how this series can be effective in addressing knowledge gaps in the various steps of the SAF implementation among states. In particular, we appreciate the participation of those from Asia-Pacific region, whom I recognize would be past your regular working hours. So today's session, the objective of today's session, which is SAF production technologies and certification, is to provide participants with an understanding of the specification of Aviation Turbine Fuel, ATF, the process to approve new pathways for fuel production, and its use on aircraft. As you can see from the agenda, we will spend some time reviewing definitions of aviation fuels. It's important we all understand what we are talking about. Then production and processes toward fuels approval, main challenges, and some prospects on how fuel certification processes could evolve in the future before moving into, of course, a session on question and answers where we can interact with you and take out your doubts. Today, we are very pleased to count on the expertise of three ACT-SAF partners: Mr. Ross Walker from Airbus, Mr. Mark Hussain from the US Federal Aviation Administration, and Mr. Nicholas Schuland from Safran. They have very kindly volunteered to share their knowledge, expertise, and experience with states as part of the ACT-SAF series. A big thank for your cooperation. It is a pleasure, really a pleasure having you here today. I hope you will make full use of this session to ask questions, to clarify on matters pertaining to SAF, production and certification, of course, related issues. And we really encourage every participant to make today's training as interactive as possible. Between each session, we will take time for questions. You are mostly welcome to raise your hand with the dedicated Zoom button and take the floor. Submitting questions in the chat is also much welcome. I also wish to insist that there are no prerequisites in terms of knowledge from participants, and therefore all questions are perfectly valid questions. Before I hand the time over to Bruno Silva, our ICAO fuel officer, who will give you a short update on the ACT-SAF platform and will also moderate the session thereafter, let me recognize the great work done by Dr. Neil Dixon, our Chief Environmental Standards, and the SAF team in making the SAF series a reality. Our objective here is really to prepare those sessions as informative and as practical as possible. And this is why we directly involved as speakers our ACT-SAF partners that are really doing it. And we welcome any suggestions on how we might take this series even further. So if we can make it better, let us know. And with that, I wish you all an excellent session ahead. And Bruno, the floor is yours.
Thank you, Jane. So as we have done like on the last series, like I'll provide some quick updates on the ACT-SAF. Where do we stand since the last time we spoke a month ago? So again, like all the updates are provided in our ACT-SAF platform. So we are uploading the videos and the presentations of this ACT-SAF series on the website. We have received some feedback that it was a bit hard to find the videos. Now I think it's very clearly marked there, like if you want to watch the presentations after, it's now available there on our website. You can go to the next slide. Feasibility studies. So we are now foreseeing the development of many feasibility studies under ACT-SAF. So we have already announced like the 3 new feasibility studies are under development under the existing IKU project for Zimbabwe, Cote d'Ivoire, and Cabo Verde. And we have financial resources that have been provided by Cote d'Ivoire, France, Netherlands, and the European Commission. And these resources will allow several additional feasibility studies. We're now in conversations to define like who will be the beneficiaries of these feasibility studies, and we hope to have news very soon. We're also structuring a project with the World Bank, and we also want to share some news on that soon. And we are also noting like that many partners, ACT-SAF partners, are also pursuing feasibility studies, and this is also very welcome as well. So very soon we'll have like a lot of feasibility studies coming to be developed and published in the near term. So what we are also doing now is to develop a template for these feasibility studies so that we facilitate like the comparability between the results, like we can compare the results between different feasibility studies. And it will also facilitate the outreach of the results so that people know where to find information on these feasibility studies. And with an harmonized structure, this is going to be facilitated. We also received some feedback like that people wanted to have more details like on what will be the projects following the feasibility studies. So we always start with the feasibility study to check if it's feasible or not to develop a SAF industry in a state. But after that, we're also foreseeing like projects to support policy implementation, as so there are many policies that are available to support SAF development. So here are some categories that we have listed in our ICAO guidance on potential policies and coordinated approaches for the development and deployment of sustainable aviation fuel. And there is this question like, what is the best policy for a specific state situation? And we will support states like to identify what is the best solution in terms of policy, and also support states to implement a policy framework if that's the case. Next slide, please. So, and we once again, like once identified the feasibility of SAF production in a state, reminding of the ACT-SAF series, like where we're talking about sustainability. So all the elements of a SAF supply chain needs to be certified, since the feedstock production from the farms and the distribution of the feedstock, the SAF production plant or the refinery, and up to the SAF blending point. Everything needs to be certified under CORSIA standards. So once we identify these potentials on the states, we also foresee like providing support to states ongoing through these certification process. And that's where we think like that the group of ACT-SAF partners will be very instrumental in providing support to states in performing such certification. So and again, so a key request that we have received since the beginning is the conceptual training on SAF. So on today's session, we will talk about SAF production technology and certification. This will be complementing what we had on the last series, like we're talking about sustainability certification. Today, we'll really go on to the technical certification, how to ensure that the technologies to produce SAF are safe for use in aircraft. And as Jane said, like these are the current list of additional series that we're foreseeing, but any feedback is welcome for us. This is not final yet. We're accepting feedback and we can adjust these as needed. So with that, next slide. So with that, I would like to hand over the floor to our first speaker, Mr. Ross Walker from Airbus, who will start like on these 4 first items here of the agenda, talk about aviation fuel terms and acronyms. What is aviation turbine fuel? How is aviation turbine fuel produced and controlled? And we'll provide an overview of aviation industry processes for assessing, controlling, and approving new feedstocks and processes for aviation turbine fuel production. So, Ross, the floor is yours then.
Okay, thank you very much, Bruno. I'm Ross Walker. I work for Airbus. I've been working on fuel specifications for about 30 years now, and I would try and impart some of the information I have. Next slide, please. First of all, I'd like to start off with some definitions. There are lots of acronyms that go around. From an aircraft design point of view, we are mainly concerned about safety and certification to ensure that safety of the aircraft, and the fuel is one of the key components for that. What we call it is aviation turbine fuel or jet fuel. And when we start producing fuels from non-petroleum products, we call them synthetic aviation turbine fuels. And they're composed of petroleum fuels at the moment with a blend of a synthetic blend component, which can be a sustainable part or not. But the fuel specifications do not deal with sustainability at all. The fuel specifications are primarily there to ensure safety of the aircraft and its operations. SAF is a term that's often used for sustainable aviation fuels, and the sustainable synthetic aviation turbine fuel can be SAF. And in ICAO, you also have the low carbon aviation fuels. My talk today will be about synthetic aviation turbine fuels and how we ensure they are safe for operations for the aircraft. Next slide, please. So what is ATF? Next slide. So ATF, aviation turbine fuel or jet fuel, is a commodity traded around the world, have minimum requirements, and during trading, it is basically controlled by two specifications, either ASTM D1655 Jet A fuel and Jet A1 fuel, or DEFSTAN 09091 Jet A1 fuel. These two fuel specifications are the ones which the industry works with. And wherever an aircraft flies around the world, it needs to pick up the same fuel. If it picks up a fuel that is different, then that can affect the safety and the operation of the aircraft. Next slide, please. Aviation turbine fuel. It's a hydrocarbon in the C8 to C16 range. It doesn't have a precise chemical composition. It's primarily a distilled crude oil, is composed of paraffins, naphthenes, and aromatics. I put aromatics here in a red box because that is one of the subjects we have to deal with when we start synthesizing fuels, because not all means of synthesizing will produce aromatics, and as I will explain later, they are required for aviation fuels. On the right, you see a table there, which is a list of requirements that we check for each batch of fuel. But if we go to the next slide, please. The thing is that the list of properties that we check is not everything that we require within jet fuel. Many of the properties are, such as specific energy, density, and volatility. Those are things that we can check, but other properties within jet fuel made from petroleum sources are what we call inherent. They are there because it is produced and been produced for many years in a set way, and we know that the electrical permittivity of the fuel will be within a certain range, and that is critical for fuel gauging in that particular aspect. There are other properties within the fuel which are inherent and important for the safety and security of the aircraft that we don't actually measure, but are basically there because of the production processes that we use. Next slide, please. So now I would like to talk about how we produce jet fuels. We all know that jet fuel is produced from petroleum and crude oils, but not all crude oils are the same. You can see here visually that these are 6 different crude oils, and they visually look different. But they all can be used to reduce jet fuels. Next slide, please. 2 key differences that are within the crude oils is the amount of sulfur in them and also the viscosity. And depending on the sulfur level and the viscosity, the production processes used to actually transform them into different fuels and products can vary significantly. Some products, the light fuel on the bottom right-hand side, these oils tend to be quite easy to manipulate manipulate and to transform into products. The products, the crude oils on the top left of this chart, with a heavy sulfur and very high viscosity, tend to be more expensive to produce. So there are lots of different processes used. And if we look at the next slide, we can see that if we did a straight distillation, i.e. that's just putting the fuel into a distillery, which would then heat up the liquids, and the vapors would be taken off at different temperatures, depending on the origin of the crude oil, how thick it is, the viscosity, what its sulfur content is, we would get different products out. If you could tap the next slide, please, next action, there we go. This last column is showing you what the actual market needs, as opposed to the previous 5 columns, which show you what products would be produced just by straight distillation. And you can see that we would not achieve the products we want. So therefore, we have to do more than straight distillation, and we have to synthesize the jet fuels and the other fuels by other means, using the crude oil. So if we go to the next slide, I'm still talking about crude oil. I'm not talking about fuels which could be substantially sustainable from renewable sources. This is crude oil production, and you can see there, very small perhaps, but there are multiple pathways we use to actually break down different components and reassemble the different components within the hydrocarbons to make the products we need. I picked out on the right-hand side 2 aviation fuels, avgas and aviation jet fuel. Aviation jet fuel, as we're talking about today. These products can be made by multiple processes, even petroleum sources. So synthesizing fuels is something we have done for a significant period of time and safely produce jet fuels this way. If we can go to the next slide. As I say, we've been producing fuels either by straight hydroprocessing or by straight distillation, or by hydroprocessing or synthesizing is another way of saying that, since 1945 to 1999. And there's always using petroleum fuels. In 1999, there was a major change in that we allowed the production of jet fuels from non-petroleum sources. This was done through a process called Fischer-Tropsch. It took about 5 or 6 years of very intense investigation and study by the producer of the fuel in collaboration with all the airframers and engine manufacturers to verify that this new production method was fit for purpose and would not affect the operation of the aircraft. But the fuel that came out at the end is a jet fuel, a Jet A or Jet A1 fuel. It was limited to a 50% blend with existing petroleum at that time, due to concerns about certain properties, and one of those being the aromatics, which I mentioned earlier, which is important for functioning, particularly of fuel gauging systems and some of the joints and sills on the aircraft. If we go to the next slide, please. When we got to 2009, we'd already approved 100% synthetic fuel from using the Fischer-Tropsch process, but it was restricted to one specific refinery in South Africa and was not generally available for every reduced fuels in that way. This was a catalyst to us actually formalizing more precisely the process for approving fuels, which is a process which we call ASTM D4054, and also another means of actually documenting the approval process. Rather than cluttering up the existing specification with lots of different approvals, we created a brand new specification called ASTM D7566, and within that specification, we started putting annexes in. The first one was the Fischer-Tropsch process, which was expanded to going beyond production in South Africa to a wider approval that can use various means of production, going from existing fossil sources such as coal or natural gas, but also to renewable biomass, which could be sustainable. And in 2011, we approved the second annex, which is a HEFA fuel, which is hydrotreated esters and fatty acids, which is probably the one that's been most used. Sometimes used cooking oil is transformed in this way to reduce fuels. So in 2011, we'd gone from 2 pathways to 3, and where we are today with the next slide. I won't talk through all these different processes, but you can see there are multiple different feedstocks we can use, from sugars, starches, vegetable oils, to transform fuels into jet fuel. Now, all these fuels today that are synthesized from non-petroleum sources require that we blend them. This blending is to ensure we have the correct aromatic content, and also it gives us very much confidence that the final fuel is the same as existing Jet A and Jet A1 fuel. And all these fuels are certified as Jet A and Jet A1 fuel based on 2 key specifications, ASTM D1655 and DEFSTAN 91091, which are the specifications I mentioned in my second slide, showing where fuel is available. It is important that the final product is a fuel that is listed in the aircraft documentation and certified by the airworthiness authorities as fit for purpose for the aircraft to ensure the safety of the aircraft and operations. And that is the purpose of the specification, safety and of the operation of the aircraft. If we go to the next slide, this is something you can look at later, or you can go to the actual document, ASTM D7566, which will list the 7 pathways which we have now approved for use to produce Jet A and Jet A1 fuel. There are also 2 other methods to produce fuel, which are directly within the 2 specifications I mentioned, that actually allow you to blend non-petroleum oils, such as vegetable oils, with crude oil at the initial point of production. And so therefore they go into the normal production process to produce a Jet A and Jet A1 fuel without a blending requirement. But normally there is a restriction at the present time of around 5% of vegetable or non-petroleum oils to make those fuels. If we go to the next slide, this slide is trying to explain what I mean by blending and why we have the requirement for blending. The top wiggly line, you may call it, is actually showing the hydrocarbon distribution of a Jet A1 fuel produced from a petroleum source, 100% petroleum. The bottom green line is one of the fuels that we use that is derived from a vegetable matter that is synthesized, a synthesized blend component. We call it a blend component at this time and not a SAF or sustainable aviation fuel. It's simply a simplified blend component because it's not certified for use on the aircraft. But if we blend the green line with the blue line, we end up with the red line. And that is a sustainable aviation turbine fuel. And if you compare the red line with the blue line, they are very similar, whereas the green line has a significant difference to the blue line. One of those key components I mentioned again, I'm repeating myself, is the aromatics. Aromatics are something which we've always controlled in jet fuel. We've always limited what the maximum level of jet aromatics is within jet fuel. But we know that because it's inherent within jet fuel production from petroleum sources, we've never had to put a minimum value in. But when we produce fuels from synthetic processes, then not all processes produce aromatics. And therefore, we've had to put in place a requirement that there is a minimum aromatic content within jet fuels that are made from non-petroleum sources. And this is a key criteria that limits how much we can actually use sustainable or synthetic feedstocks to produce jet fuel. The actual blending ratios are specified in the ASTM D7566 document because they will vary depending on which feedstock and which process you are using to produce the fuels. If we go to the next slide, then I will give you an overview of where we are today. Next slide, please. So what I was talking about, I've talked about how we produce normal petroleum-derived fuels, that there's a varied processes we use. We actually break down and we synthesize much of the petroleum jet fuel that we have today. But when we go to synthesizing fuels from non-petroleum sources, we have to have a very clear and precise process, ASTM D4054. And Mark Ramazan in the next part of this presentation would explain clearly what that process is, who's involved, and how we achieve certification through that process. A second document I mentioned was the D7566. This is a document which allows us to actually categorize and define precisely each processes in the forms of annexes within this document. As I said, there are 7 annexes allowing you 7 different pathways which enable you to produce potentially not just synthetic fuels, but synthetic fuels that could be sustainable. But neither of these documents are approved for flight. The D7566 fuel needs to be recertified as either ASTM D1655 or DEFSTAN 91091, which are listed in aircraft flight documentation, not just for Airbus, but for other aircraft producers such as Boeing, Bombardier, Embraer. And it's only at this point is it approved for flight. And it's based purely on the safety requirements for the aircraft that is approval is given. So that was a very rapid explanation of what jet fuel is, how we synthesize, or options we have for synthesizing jet fuel from non-petroleum sources, which could potentially be sustainable. And I think now that Mark Ramazan will explain later more precisely the 2 documents there in the red, the 4054 and 7566 documents. And if you have any questions, I'm open to take them.
Thank you very much, Ross, for kicking off this session. Okay, yeah, so let's move to the rest of the presentation then. Thank you, Mark.
Yes, hi, and hello, everybody. My name is Mark Ramazan. I work for the U.S. FAA, Federal Aviation Administration, and I'm also the chairman of the ASTM Aviation Fuel Committee. And that's important. The ASTM committee is an industry committee. The FAA is obviously a government regulatory agency. And it's important to understand that aviation fuel is primarily controlled by the industry. So for me as a regulator, it's important for me to have a hand or hand and a foot, both in what industry is doing and what the FAA is doing. The other thing I want to mention is I appreciate this opportunity for my ICAO to have this. It's really a wonderful opportunity to have this global presentation, people all over the world, because we all really need to understand that jet fuel is a global product. It must be the same wherever Airbus or Embraer or Bombardier airplanes fly. The fuel they load at an airport in a different country or a different continent needs to be pretty much the same. So, Ross talked about safety. Safety is critical. I'm only going to talk about safety. I'm not going to talk about sustainability, even though I know everybody's interested in sustainability and carbon emissions. My focus here is strictly on safety. Next slide, please. Next, please. So the way we control fuel, and this is very important, is by a fuel specification, which is they're typically industry documents. They're also military documents. Next, please. But there's different specifications, and they're all controlling what we call Jet A or Jet A1 fuel. It's the same fuel. Slow down, please. So we control fuel with a fuel specification. The aircraft engine companies, such as Pratt & Whitney or Rolls-Royce or GE, they include the fuel definition or the fuel specification as an operating limitation. And then that operating limitation, next please, flows up to the aircraft operating limitations. So as part of the aircraft design, there is a limitation that says you must use Jet A or Jet A1 fuel in very simple terms, but it may define properties or the specification, but really what all it says is you must use Jet A or Jet A1 fuel. Next, please. So this is done during the certification of the engine and aircraft. And then you send the aircraft out to airlines, let's say. Next, please. The airlines, in accordance with the regulations from EASA, from Transport Canada, from the FAA, the airlines can only use the fuel that the airplane and engine manufacturers say they must use. And that's called an operating limitation. And next, please. And next, please. So what this means is, if you look at this whole picture, is that the airworthiness authorities, again, FAA, EASA, Transport Canada, ANAC in Brazil, JCAB in Japan, we don't certify fuel as a product. We don't certify fuel as a part of the airplane. We certify airplanes and engines to operate on a specified fuel. And that's very important. That drives a lot of things that I'm going to talk about in the next couple slides. Next, please. And it's important to note that the airline is where the airworthiness authorities apply their regulatory oversight. You know, they go to the airline and say, "Are you sure are you only using the fuel that Airbus or Boeing says you're supposed to use?" That's but nothing upstream of that, where the fuel is made, how it's handled, quality checks. None of that is under the oversight of the aviation regulatory authorities. Again, something that is very kind of difficult to understand. Next slide, please. So this all ties into how do we approve these fuels. And Ross, thankfully, already gave you the definition for SATF, synthetic aviation turbine fuels. Notice I'm not using SAF here. I'm saying SATF because not all SATFs are SAFs, but all SAFs are SATF. Anyway, so we start off with block one. And as I just talked about, all the airplanes are approved to operate on, next please, Jet A fuel. Or Jet A1 fuel. That's their operating limitation. But they're all approved to operate on the same fuel. Next, please. So what we did when we were trying to figure out a way to evaluate SAFs or SATFs, we developed a process, and it's defined by an ASTM standard, D4054. That's our evaluation process. It tells you what tests you need to conduct with a lot of other information in it. And really, all that's doing, all that document is trying to do is to compare the fuel made from, let's say, renewable resources like sugar or vegetable oils, whether or not that fuel is essentially identical to jet fuel made from petroleum. That's what that process is trying to do. And if, next please, if the determination or conclusion is, and this is done with the aircraft and engine manufacturers, it's a very rigorous process. I'll explain that in the next slide. But if a determination is made by the aviation fuel community in general, all the stakeholders that it is, yes, it is the same fuel, then we add it to our drop-in fuel specification, which is ASTM D7566. And we, as Ross mentioned, we add these as annexes because, next please, because we right now we require blending with conventional jet fuel to get a complete jet fuel. These are subsets of jet fuel for the most part, and I'll explain that again later. Yeah, okay, good. My timer's going. Next, please. And what we call the fuel products defined in the annexes, we call them synthetic blend components, SBCs. I think Ross also mentioned that. Thank you, Ross. Next, please. And then you blend it. I just kind of talked about this. That's how you make SATF. Next, please. Ross also mentioned how many years he's worked in aviation fuel, and you notice I skipped that part. I don't want to admit that part, but I'll just say it's almost as long as Ross. So I know almost as much as he does. So moving from block 3 to block 4, back up please. So block 4, since we've already proven the fuel is Jet A fuel, it's just Jet A fuel. It's determined it's equivalent to the conventional jet fuel specification. Because it's equivalent, and there's wording in both specs to sort of lock that in. Next, please. Because it's equivalent, it brings you back to block 1. It meets the operating limitations. So you can use it without any additional approval after you get the specification defined. Next, please. So what that means is getting your conversion pathway, your SAF, whatever you want to call it, into our drop-in fuel spec, that equals approval to fly, which is, and it's quite an accomplishment that we in industry collectively worked out this process. And it's a very rigorous process, which I'll explain. You know, it's going to be safe. Whatever we approve is absolutely safe. But that's it. That's why you hear so many companies talk about getting ASTM approval. It's not really ASTM approval. It's really getting their own ASTM specification annex. Next slide, please. So next, please. So let's focus on the evaluation process, because that's really the heart of this whole process I talked about, the D4054 evaluation process. Next slide, please. So what this process does in very simple terms, next, please. Next, we'll do this quickly. Next. So what it does, it's working backwards. It's trying to determine if the new fuel, and it's not really new fuel, but I use that term here, fits the existing fleet of engines and airplanes. And I used to work for 2 engine manufacturers, and I always tend to forget the airplane. So excuse me for this slide. Sorry, Ross. But this really applies to airplanes as much as engines. The idea is to make the fuel fit the airplane. Next, please. And if it does, we call that a drop-in fuel. So you don't need to make any changes to the airplanes or engines. You need to put a lot of work into making the fuel and getting it right. But once you do that, you can just use it on the existing fleet of airplanes all over the world. Again, Embraer airplanes, de Havilland airplanes, Airbus airplanes, Airbus helicopters. Next, please. So here's the evaluation process. The first part of it is an evaluation of fuel properties. Next, please. And then a report gets issued. Next, please. And then there's a collective review of the data. And this is a very rigorous review, trust me. Where all a team of engine and aircraft manufacturers, which has grown considerably in the last couple of years because of the interest in SAF, and myself as part of the FAA and EASA sometimes participates, Transport Canada might get involved. We review the data. We make sure, first we determine, does this look like a Jet A fuel? And then secondly, we determine, is there any additional testing required? Just to double check things that we might not be sure about. Next, please. And if there is additional testing required, then we get into more expensive and more testing that requires a lot more fuel, combustor rig testing, engine testing, fuel nozzle rig testing. These are more expensive tests, but you know, they have been necessary in some cases, and they provide important data. Next, please. Next, please. And we go through another similar final review. Next, please. And then finally, when the whatever national airworthiness authorities are involved agree, the engine aircraft manufacturers all agree, they give it a thumbs up. Then we say, okay, this looks like a jet fuel. This will be safe on our products. That's the important thing. Then after all that, next, please. Then it finally goes to a balloting process at ASTM, where the rest of the stakeholders, the rest of the aviation fuel industry stakeholders get to review the data. And there are handlers of fuel, there are pipeline companies, there are companies that make ground filtration systems, which you may all be aware of. There's a lot of people that support maintaining the quality and handling and distribution of fuel that, you know, should look at the data in case there's something about the fuel that we missed and that it's important in their area. Next, please. And if everybody finally determines the fuel is essentially Jet A fuel, it's no different, it's going to perform the same, it gets added to our drop-in fuel spec. Next, please. So the FAA has done, next, please. We've created kind of a virtual clearinghouse. And basically what this is, next, please. Think of it as a black box. I mean, it's a group of us that coordinate, manage, and conduct the evaluation process to help these companies, which in many cases are new venture, not very low capitalized companies, to help them get through the process. Next, please. So the idea is that the company delivers us a minimum amount of fuel, 50 to 100 gallons of fuel, and then we coordinate it. Next, please. And out the other end comes that research report that I talked about on the previous slide. So it facilitates the process, it subsidizes it. Next, please. The FAA provides funding to help with the testing and help with the OEMs to review the the engine aircraft manufacturers to review all the data. So, so again, it just facilitates the process and makes it easier for these companies to get through the process. Next, please. Let's cost share. Next, please. So using the process and the concepts I just talked about, what have we accomplished over the years? Next, please. It started with CAFE. Next, please. The Commercial Aviation Alternative Fuel Initiative. You should all go look at that website. There's a lot of good information on what you are interested in, SAF and SAT-SAF, a lot of good information. It started with that to kind of, as a coalition, to get the industry players together to figure out how to go down this road that I showed here. Next, please. We issued the drop-in fuel spec in 2009. Next, please. Next, please. That had the first annex in it. Ross talked about this, Fisher-Tropsch. We decided to work on that first because there had been a lot of work done before that. It's a long story. I'm not going to get into it. But that was our first annex. That was our first drop-in fuel. And ironically, that fuel, you know, is most of the experiences that fuel made from coal, which is not a SAF. You know, coal is not sustainable. But because back then in 2006, 2009, there was a lot of interest in supply security and the concern with petroleum reserves running out, more so than the environmental concern, interestingly enough. That's kind of how this all started. But Fisher-Tropsch, for sake of full disclosure, can also be made from renewable products, and there are companies working on that right now. Next, please. Next, please. Yeah, so the little circle there with the A1, and that represents the annex number in the drop-in fuel spec. 2009, we issued, next please, the evaluation process. We issued a standard, and we were following that before that, but we finally got it issued and documented. Next, please. And then over the succeeding years, you can just kind of keep going. The succeeding years, we issued several annexes. So, you know, we've been going through and we worked, I promise we worked all the companies involved in the fuels and these annexes. We kind of, so we say in the United States, we worked them through the ringer. You know, they had to provide a lot of data. Next, please. You know, so we've accomplished a lot. We've issued 7 different annexes. There are varying percentages of blends. They blend at different percentages, either 50 or 10%. The fuels are made from different feedstocks. There are different conversion processes. You know, there was a lot of data for all these. There was a lot of work put in. And again, I assure you that safety was the paramount concern. And these fuels produced by these conversion processes are Jet A fuel, the same Jet A fuel that, you know, you see pumped in your airplane when you're waiting by the gate and getting ready to take off. It's the same fuel. Next, please. Okay, so let's talk about, we had a question. Everybody's interested in 100% SAF. So let's talk about how we get there. Next, please. So first we need to understand this concept of blending. Ross mentioned it, I've mentioned it. So how do we do it now with the existing annexes? Next, please. So first you have conventional jet fuel made to the conventional jet fuel specification. That's being done everywhere. And next, please. And then next, please. And then next you have to make the synthetic blending component. That's done in a completely separate process stream. Next, please. So now you have, on one hand, back up one, please. So now you have a synthetic blending component on one hand, and you have conventional jet fuel on the other. And this is like that Reese's peanut butter cup commercial where the 2 trucks crash together, and one has chocolate, one has peanut butter, and they put them together and make Reese's peanut butter cups. But next, please. Then you blend them. And then next, please. That produces what we call an SAT-SAF, synthetic aviation turbine fuel. You can blend up to 50%. Next, please. And that's all. That's the blending. The blending step is covered in the drop-in fuel spec, as well as the production of the synthetic blending component is also covered in the drop-in fuel spec. The production of the conventional fuel is covered by current conventional fuel specs. So now you understand that they need to be blended right now. And I'm going to talk a little bit about why they need to be blended. Ross also touched on that. Next, please. And that, as I've said many times, it is Jet A fuel. It's important to understand that it's the same fuel, tastes the same, smells the same, looks the same. Next, please. So we need to look at the composition. Again, Ross talked about that a little. So the composition of a jet fuel is made up of different hydrocarbon classes, compound classes. We have the names there. They have different structures. They're all made of hydrogen and carbon and hydrogen. And that's what fuel's made from. But these have different structures, different sizes, let's call it. And those different structures and different sizes contribute to the properties of jet fuel, which are important and make the jet fuel work in the engine properly and work in the airplane. Next, please. So you have that whole formulation. And then let's look at the first annex. You notice the annex and think of the full formulation as a pizza. The first annex, Fischer-Tropsch, is missing one of the slices of the pizza. Ross talked about it. It's missing aromatics. That's a unique type hydrocarbon molecule. So it's not, so next, please. So think of it as a compositional subset of jet fuel. It's not the complete jet fuel, but it's a piece of it. Next, please. HEFA, same exact thing. Next, please. Next, please. Now, SIP, which is synthesized isoparaffins, notice that's just a small pizza slice. That's not almost the whole pizza. In other words, the whole rest of the pizza is missing. You only have one slice there, the isoparaffins. So that's only limited to 10% blending. You're going to figure out as I talk how we come up with the blending percentages. The first two, you can blend up to 50% because it's easier just to fill in that one slice of pizza. The third one, and I'd say 3, you can only blend at 10% because you need a lot more slices of pizza to complete the jet fuel formulation. Next, please. Annex A4, this one's different. Next, please. This is what we call a fully formulated jet fuel. It's the whole pizza. So why do we only approve it at 50%? Why does it have to be blended? The reason is we want to be conservative. We don't want to let an airplane fly across the Pacific Ocean or Atlantic Ocean on 100% SAF. Again, that's what we're talking about here until we get more experience. So right now there's a limit. You can only use up to 50% of it blended with conventional jet fuel. Next, please. Annex A5, same thing, missing the aromatic slice of the pizza. Next, please. Annex A6, here we have another fully formulated one. Same thing applies. We only limit it to 50% because we want to be conservative and we want to make sure we're safe. Next, please. And the last annex is the same thing. It's compositional subset. This one's a little, I wasn't going to get into it. It's only limited to 10% because we introduced sort of what we call a light or a streamlined evaluation program where less data was required. But the trade-off was we said, okay, you can provide less data, but we're only going to approve you at 10%. But it still is only missing one slice of the pizza, the aromatics. That's why Ross talked about that. That's why aromatics are so important. Right now, we don't have an annex for aromatics. We don't have that missing piece right now, and I'll talk about that in a second. Next, please. So how do we approve? How do we put in place a specification for 100% SAF? There are 3 ways, and this follows on what I just talked about. So first is, next, please. You blend one of those compositional subset annexes with a fully formulated annex. Next, please. So you take an annex like A2, HEFA, that's missing the aromatic slice of the pizza, and you blend it with CHJ, which is the whole pizza. And depending on the blend percentage, you've got to get that right. We're not going to get into that now. But you end up with a complete pizza there on the right. Next, please. The second approach is to blend one of the compositional subsets with a different compositional subset annex. Next, please. And here's what I talked about. We don't have an annex that makes just an aromatic blending stream, but it's in process. There's a company called Virent working on it. They're close to approval, but it hasn't been approved yet. When they're approved, they will be that gray slice of pizza. And that will allow blending with HEFA, for example, or Fischer-Tropsch to make your fully formulated SATF, your complete pizza. I hope pizza is a global product, hopefully, but I believe it is. I think everybody in the world has tried pizza. Next, please. The third approach is to allow use of one of those fully formulated annexes. Next, please. With the addition of additional properties, I'm not going to get into that, but we would need to add some additional properties to the specification and allow use of that without having to blend with anything else. So I want to let everybody know that we're working on this at ASTM. We put a lot of work into structure, revising and coming up with the wording in the specification, which is very important because remember, the specification controls the fuel from where it's made at the refinery or wherever it's made, all the way through the supply chain to the wing of the airplane. So it's very, very important we get it right. So we've done this. We've got it kind of written. Now we have to see how much data we need and review with ASTM and go through the whole process. But we're working on it. To sum it up, we know how to do it. We just have to get it into the specification, and we're working on that. Next, please. Co-processing. Again, there were questions on this. Ross touched on it. Next, please. So let's take a look. Here's the blending, scheme I showed you how we do it now with the drop-in fuel spec D7566. And remember, I just saw a question, chat come up. Remember, everything I'm talking about here, the pizza, the fully formulated jet fuel, anything that we approve, and this is very, very important, I should be very clear on this, is Jet A fuel. You don't need to do anything to the existing fleet of thousands and thousands of airplanes out there, helicopters with jet turboshafts, little turboprops like Cessna Caravans, big airliners like Airbus A380s or Airbus A350s or Boeing airplanes. You don't need to do anything. This is the same fuel. And because of that slide I put up with the 4 boxes about the approval process, you don't need to approve the airplanes to run on it once, but only after we get done and put it in the specification. No additional approval required. So effectively, right now, all airplanes are approved to operate on 100% SAF if we get it in the specification the way I just talked about, doing everything I've talked about in this presentation. It's no different. It's nothing special. Once we're done with the approval process. Before that, any discussion on 100% SAF, you can't use it. We're not sure about it. We don't have the data. Everything is data driven. Next, please. So back on co-processing. So co-processing, what we do is forget about the bottom path there with the annex synthetic blend component. Next, please. We do is we take feedstocks that have been used to make the synthetic blend components. Again, think of things like vegetable oils, algae oil, plant oils, and then in the case of Fischer tropes, biomass, whatever. You take the feedstock and you treat it a little or whatever, you get it ready, and you insert it into the conventional jet fuel production process. I just realized I should put a big X on that bottom box because we don't need that right now, and a big X on the right-hand box. So just imagine 2 big X's are flying in. I like things to fly in, as you can see. I forgot that, but just imagine 2 big X's flying in on the right-hand box and the bottom box. And we're only looking at the top box. So you just blend in that feedstock, next please, but only up to 5%. And then you go through normal refinery processes, basically hydroprocessing. And then next please. And then out of the refinery comes what we call co-processed jet fuel. The reality is right now, because of the 5% limit, and because of the weight or the size of these natural oils that are used, typically most of it, because it's going into a refinery. Remember, a refinery makes more than jet fuel, as Ross talked about, right? It makes diesel fuel, it makes gasoline, makes heating oil. Most of this renewable feedstock will end up in the diesel and heating oil because it's a heavier weight. But we've approved it, so because just in the event that any small percentage gets in the jet fuel, we need to evaluate it and approve it again for safety, right? And as Ross said, we are working on, there are currently different versions of this are being worked at ASTM. There is a task force working on increasing this percentage to maybe 30%, but they're going to need data, and they're working on collecting the data. They're going to review with the engine aircraft manufacturers, like I talked about before. So in order for it to get approved at a higher percentage, they will need to go through that approval process. But this is where it stands now. Next, please. Next, please. Okay. Just a quick slide. Let me check my time here. I'm over time by 2 minutes. I'm sorry. Next slide, please. Just real quickly, I mentioned this earlier. Next, please. Next, please. Okay, I talked about it earlier that the FAA, EASA, ANAC, Transport Canada, JCAB, they focus on the airline. They walk up to the airline and say, are you using the fuel that Boeing, Airbus, Embraer says you're supposed to use? Next, please. So, but as I said, the way we've worked out the approval process with SATFs, once it gets into that specification, it is part of what's already been approved. So there's no additional approval for the airline to do that, as long as they adhere to, you know, the operating limitations, as long as they're only using jet A fuel. It gets a little confusing, but there is no additional approval required because we do all the work as part of the industry and conclude and make a determination that the SATF is jet A fuel, so it's already approved. Next, please. But upstream, and this is, I mentioned this at the beginning of the presentation, upstream, fuel, the whole path that fuel travels. Next, please. It's all really under industry oversight because we at the FAA or EASA, we don't get involved. We don't go talk to ExxonMobil or Shell or Neste or Total, for example, in France. We don't go talk to them or audit them, or we don't have any regulatory oversight to them. It's all under the oversight of industry. And it's evolved. You got to understand, this has evolved over 70 years. We've been using jet fuel. And it's evolved because we have very big companies making a lot of this fuel. And there's a lot of focus on safety and controlling it to the specifications. And everybody recognizes how, especially with aviation fuel, how important it is for safety. So it's worked. I mean, think about it. Think about, you know, we move 90 billion gallons of jet fuel a year globally, 25 billions in the US alone, 25 billion gallons in the US alone. And think of how many airplane flights all of you have taken. Have you ever worried about the fuel they were putting in the airplane? And think of how fast they have to move the fuel and fuel the airplane. And there's nobody there checking it when they're putting it in the airplane. The reason for that is we have all these upstream quality control procedures and standards in place that everybody adheres to. And the sort of a final comment is, because of that, that's why we worked the approval of SATFs and SAF into this existing structure and procedures we have. That's the whole concept here with drop-in fuel. Working into the existing infrastructure we have, and it'll be safe because we know it works. Next, please. Okay, I was a little over. I'm sorry about that. I guess I'll take questions now. And I'm sorry, it was 5 minutes over.
Well, thank you, Mark. But I guess it was worth it. Like, great presentation. Like, I really like your pizza analogy. Like, it's very makes it very clear to see the difference. And also, like, what you just highlighted, like, this is really a global process, right? Like, you highlighted, of course, like your FAA experience, but it is a process that works like globally, right? Like, we refuel aircraft like all over the globe, like, and it is safe. Like, the safety is really ensured. So with that, like, I think we can, I don't see any other questions here. So I think we can hand it over to our last speaker, Mr. Nicolas Joulin from SAFRAN, who will talk about the current challenges on SATF certification and the future evolution of SATF certification processes.
I like it.
Nicolas, okay, we can see you. Okay,
yeah.
Thank you.
Thank you very much to give me the opportunity to present you our vision. So I'm Nicolas Joulin from SAFRAN. I'm a fellow fuel expert. I've got little less experience than my previous colleague. I'm working in the field of fuel for something like 20 years, previously in the oil industry and then in SAFRAN, which is an engine and fuel system manufacturer. I will just make a small presentation as a conclusion of all what have been already presented in order to show you that the certification process of SAF, as you've seen it, is very efficient, it's very safe. We can say, okay, we have already pathways that are certified. We have a system that is working very well. So now everything is good, we don't have to change anything. I will just show you that some improvement are still needed, and that we have some improvement pathways and some work still being done in order to certify new pathway, to go to 100% SAF, and to increase the efficiency of the certification process. So if we go to next slide, please. Okay. First of all, a very important thing is that when we look at the ICAO long-term aspirational goals that have been accepted in late 2022, we see several scenarios that have been put on the table, and all these scenarios rely on a massive ramp-up of SAF. All these scenarios. Such ramp-up implies really an increase of the production of SAF, an increase of the use of SAF everywhere in the world, so that the certification process is key in order to allow these scenarios to be reached. So such ramp-up implies, first of all, the continuous qualification of new SAF pathway. We could say, okay, we have already 7 pathways that are certified, so it's sufficient. Let's stay like that. But clearly, no, we have to certify new pathway in order to be able to use any feedstock present in any part of the world, and to be able to transform it in an efficient way in a fuel that can be used in any aircraft in this country. So that enlarging the scope of the biomass that can be used, or the feedstock that can be used in order to produce SAF, is key in order to allow this deployment in any country in the world. And the second implication of such ramp-up is that we will have to go to high blending ratio, and we'll have to go up to 100% compatibility of all the aircraft with the fuel. We could say, okay, why are we speaking about 100%? Because we see its long-term vision, and we are today at something like less than 0.5%. So why are we already speaking about 100%? It's because, first of all, we have to prepare the future technology, and the technology that will come on the market in the 10 years to come will, with their life duration, still be there 20 years later, so that close to 2050. So this technology will have to be compatible with the fuel that will be on the market in 2050, so that we have to be ready now in order to be able to develop this technology with the fuel that will be on the market in 2050. The second point why we are going to 100%, we are already discussing about this specification of 100%, is the fact that some application in some countries in the world already want to go in very high blending ratio. We can see, for instance, the huge pressure on environmental footprint of aviation, especially in Europe, in the US, etc., and with a focus today on specific application. And we see, for example, huge pressure on business jet. And this type of application, they really ask for high blending ratio in order to be able to fly with a reduced environmental footprint. And that's why we have 2 main work currently being done in order to go to that target. First of all, we have to go towards this 100% grade, and I will say you a few words again in just after. And the second point is, if we want to certify new pathway, then we all know that it's a complex work. We all know that it's a difficult work. So we can work on increasing the efficiency of this ASTM process. And that's why I will just show you just on the next slide. You can go next slide, please. Okay. When we speak about increasing the efficiency of previous one, please. If we go if we speak about the ASTM process efficiency, once again, and Mark already told that, but it's very important to insist on that, the goal is not to simplify or to reduce the requirement. We are asking for a huge volume of data in order to be able to give the qualification of the fuel, in order to certify that the fuel is fully compatible with all the technology. The goal here, when I speak about ASTM process efficiency, is not to reduce this requirement. It's clearly to increase the efficiency of the process by allowing the fuel producer to go more easier at the final result, in order to be able to show the compatibility of the fuel with the technology. And it's very, very complex. It's very complex because I was I'll show you just 2 figures here. It's clear you don't see anything, but it's, I would say, it's not a problem. What we can say is that, first of all, fuel is critical in a lot of elements, in a lot of working condition of the aircraft and of the engine. The fuel is not only dedicated to be burned in the combustion chamber, and it's already a challenge. It is also linked to the life duration of the aircraft, the pollutant emission. It is also used in the aircraft in order to heat the cabin, in order to equilibrate the aircraft, in order to be used as a force fluid for some actioners. It has to be pumped, it has to be heated, it has to be cooled, so that the fuel chemical composition has an interaction with a lot of parts of the aircraft. So it's very complex to assess the impact of this fuel in all these parts of the aircraft. So the second very important point that is shown in the figure on the right here, we try in a previous European project called JetScreen to assess the impact of chemical composition on each, would say, running condition of the aircraft. For instance, when we say, okay, I will remove the aromatic, what is the impact? And then we put all the properties of the fuel on this table and try to make the link between the properties. And what we see is that everything is linked. If you change an element in the chemical composition of the fuel, then you will have a lot of impact. In order to simplify, when we speak about aromatic contents, for instance, everybody says, okay, aromatic have an impact on the seals. So if we remove the aromatic, we will have an impact on seals. But at the end, the impact of seals is only the emerged part of the iceberg. If you remove aromatic, you will also have an impact on the density of the fuel. You will have an impact on the volatility of the fuel. So you will have an impact on the combustion process, like the ignition of low temperature or altitude relight. Then you will also have an impact on the electrical properties, so that you will have impact on gouging system. Then you can have impact on lubricity of the fuel, etc., etc., etc. So changing the chemical composition of the fuel can have very complex impact on the engine. And that's why it's very, very complex to have this assessment. And that's why, seen from the outside, people can say, okay, it's a very complex system, it's a very complex certification process, but it is compulsory, and it is, we cannot allow to simplify it. What we can allow is to better understand all these phenomena in order to be able to go straight to the point, in order to increase the efficiency of this process. So if we go to next slide, clearly the key of this efficiency increase will be R&T. Will be an increased understanding of all the link between the fuel chemical composition and the impact in the aircraft. And just here we have two types of projects that we can quote. In the US, we have the FAA ASCENT National Jet Fuel Combustion Program, for instance, which is dedicated to the impact of the detailed chemical composition of the fuel on the combustion processes, on all the combustion processes. And I've already quoted that, the EU JetScreen project that has ended a few years ago, but that was also dedicated to the understanding and modeling of all these properties. And the more we will know the link between chemical composition of the fuel and the impact on all the parts of the aircraft, the more efficient we'll be in the certification of new fuels. So that's one point. The second way to increase the efficiency of ASTM process, and that's shown on next slide, the other way to increase the efficiency of the process is to make this clearinghouse. And Mark already told that. We are working a lot on the building of this clearinghouse at UK level, at EU level. But once again, as Mark already stated, and it's also important, the goal of the clearinghouse is not to replace ASTM. We have this ASTM process that is efficient, that is accepted by everyone, that has shown its efficiency, that has shown that it is really safe. So we have strictly no need to create new systems in order to compete with ASTM. The goal is more to put in the same table, in the same place, all the experts on different places of the world, in order to act as a guide, to act as an expert advice to the producer, in order to help them, in order to support them, in order to provide them with financing, in order to provide them with test facilities in order to make all the characterization of the fuel and then being able to bring that at ISTM level with an increased efficiency, with research reports that are very, I would say, concrete, that are very solid in order to go directly or more easily through the various steps of validation by OEM, then by the airworthiness certification system. So clearly, the clearinghouse at various places in the world, once again, is not dedicated to replace ASTM, is dedicated to support the producer in their work towards certification by ASTM process and through ASTM. If we go to the next slide, I just wanted to come back once again on the 100%. I will show you just another way. The message is the same that the one brought by Mark. Just as I speak at the end of the presentation, he spoke about pizza. I will speak about dessert with fruits, but the message is the same. We have this limit of 50% incorporation. It's really linked to the fleet compatibility. With this 50% limitation and with all the limitation that we've put through ASTM process, we are sure that all the SAF pathways are fully compatible with all the aircraft all over the world without any limitation. And that's key in the deployment of this SAF. Then if we want to go to 100%, we have two ways. The first one, as we say, is to stay within this dropping system, which means that we will formulate the fuel, we will put all the molecule in order to have a fuel that is fully compatible with all the existing fleets. It's clearly the most easy way in terms of deployment. It's the most easy way in order to be able to ensure the compatibility of all the aircraft by defining a specific chemical composition that will be compatible with all the aircraft. That's what we are doing, especially within the ASTM 100% SAF task force, in order to try to put a specification or to put a limit in this kind of fuel, to define this fuel and being able to put it on the market as soon as, I would say, 2024, 2025. So the work is advancing. We are working on that. Having said that, we can imagine another way. Another way to do that could be to say, okay, but we have, for the first time in the history of the aviation fuel, we have the availability to optimize this fuel. We have the chance to be able to potentially change this chemical composition in order to increase the efficiency of this fuel, for instance, linked to non-CO2 effect. We all know that aviation has an impact on global warming through CO2, but also through high altitude emissions, such as contrails, for instance. And these contrails are directly linked to the particles emission of the engine. And these particles emission are mainly partly linked to aromatic content of the fuel. So one way could be to say, okay, but we have already certified pathways that have no aromatic, that the slice of pizza is absent, so that this fuel could have an important potential in terms of reduction of particles of the engine and, as a consequence, on non-CO2 effect. So why won't you could we take this kind of fuel and just removing the 50% limit and go to 100% SAF without aromatic? Clearly, that would be a new grade of fuel that could be very interesting in terms of environmental footprint. But here, clearly, and that's a very important point, we are on the non-dropping pathway, which means that we are not compatible with existing fleets. We can fly. We have already demonstrated that with Airbus, with Boeing, and with others. We've already demonstrated that we could make demo flight with such a fuel, because we are still in the, I would say, the global properties of jet fuel in terms of density, in terms of volatility. We are close to a jet fuel, but we are not fully compatible with the fleet, because we have seen impact. We have seen impact on the combustion, we have seen impact on the pump system, we have seen impact on the seals, etc., etc. So that typically this kind of 100% SAF would be non-dropping, which means that it will be compatible only with dedicated aircraft, specifically developed for this kind of fuel or specifically validated for this kind of fuel. The compatibility with the whole fleet is not guaranteed, which means that such fuel will require specific logistics system, specific refueling system, double systems in the airports, etc., 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 with all the question around safety and things like that. So clearly, we don't say it won't work. We are working on that, this kind of non-dropping 100% SAF grade. There is a task force on that, but clearly we have first to demonstrate that all the benefits obtained with such grade are worth all the difficulties that they will induce in terms of logistics and things like that. If we go to the next slide. Okay, so you have the fruit after the pizza. Here are the fruits. Clearly here, what we wanted to show on this slide has been prepared by Guran Andrak from GE and Stephen Kramer from Pratt & Whitney. What we want to show here is that we have the pathway that have already been certified for 50%. The full compatibility is the red apple. It's perfectly good for health of the aircraft. Some pathways are, I would say, close to that, close to a jet fuel. So it's a green apple. It's close to an apple, but it's not very, very healthy. So we can hit it, but it's not very healthy. And some others are very different from the apple. It's the banana. So what we see is that some pathways are red apples even at 100%. That's why that's what Mark just showed you a few minutes ago. We can imagine this kind of pathway going up to 100%, and that's why I've said that we will come to a specification of 100% drop-in fuel in a few years. Is because we already have pathway that we think can be compatible with this target. So the work will be, I won't say easy, but at least we have a very good direction in order to be able to describe this specification. Other pathways clearly are not intended to go to 100% because their chemical composition is really different. So typically there is no chance that they go to 100%. And some of them, here the green apple, is close to Jet A1 but not identical. So that the gray line between drop-in and non-drop-in, we are close to a jet fuel but not compatible with existing fleet. That's typically the grade we are working at in order to say, okay, potentially this kind of fuel could be brought to 100%, but with specific aircraft dedicated for that specific aircraft, which we have demonstrated the compatibility, etc., etc. So we are non-drop-in, even if we stay in a grade close to jet fuel. So it's not drop-in or non-drop-in. We will go to 100% drop-in fuel very quickly, and we have to work on this non-drop-in grade in order to show if there is huge benefits in this type of grade, and once again, if the benefits are worth all the difficulty that deploying a non-dropping grade would imply especially at the airport level. If you go to the next slide. Okay, so that's what I've said just a few minutes ago. So we have two task forces already created at ISTM level. The first one, which is the dropping pathways, with the chair is Guran Andrak from GE and the vice chair is Mark from FAA. And we have also a task force dedicated to what we call JETIX or other name like that, which is dedicated to evaluate the potential of the removing of 50% limit on already a certified pathway. On a longer term, we could also discuss about potentially a totally disruptive non-dropping fuel, which means, okay, if we go to non-dropping fuel linked to compatible with only specific aircraft, then could we potentially discuss about radically new grade out of typical jet fuel composition? But once again, we are at very low TRL with a very low maturity. It's only discussion that we are having today in order to say, okay, what would be the benefits of going to such disruptive pathways versus all the difficulties in terms of deployment, in terms of production ramp up, etc., etc., etc. If we go to next slide. Okay, so in order to conclude, once again, we have a process of certification that is very safe. It has been demonstrated to be very safe. So all the work today is to go to a more efficient by a better understanding of all the fuel impact on the aircraft, and by increasing, on the one side, the number of pathways that are certified in order to enlarge the type of feedstock that can be used to produce SAF, on the other way, to go to 100%, first with the dropping pathway, and then in the longer term by studying other type of pathway, non-dropping, but first of all by assessing the potential of this pathway versus the difficulties that are in use. So thank you, and if you have any question, please don't hesitate to myself, Mark, or all the person today.
Thanks, Nicolas. No, that's great presentation too. Like, and I also like it, like the fruit analogy there. Like, so in the end, like we had like very clear like explanations of this blending and 100% SAF issue, right? Like, so Ross started with the very technical like mass spectrum, then we went to the pizza, and now the fruits. So it's been really great, and I think it's now very clear to everyone. So again, thank you very much for your presentations. I guess this was very, very enlightening for everyone involved here. So with just a couple of slides here to wrap up. So so as a reminder, like we'll have this will continue now, like, so we can go to the next slide here. So today we concluded this third event of the series, and the next one we're setting up for the 23rd of March in a month, and where we'll talk about SAF market outlook and policies. So, and as we have been mentioning, like we are always subject to feedback, like, so we will be adjusting these series like as we move along and if needed. And with that, I think we can go to the next slide. And thank you very much for your participation today. Very good questions and very good presentations. And we hope to see you like in the next event. Thank you very much.